So today we'll have the class 2 of stochastic controlling communication. So before uh, doing all this, I'll just give a recap of uh, what we were doing yesterday. So first we discussed two examples on lotteries. So the first one was you have an item of 100 rupees and you pay 100 rupees to enter the lottery. Uh, Now you have an biased coin, and uh, with you get heads with probability 2/3 and you get tails with probability 1/3. If you get heads, you win 3 into 100 rupees, and if you get tails, you win nothing. Now, here what happened was the average cost, uh, average uh, winnings was 200, whereas the cost you paid to enter was 100. So you made a decision on comparing what the averages were, right? In the second example, you had the same thing, but instead of 100, you were scaled to 1 crore. And similarly, you pay 1 crore to enter the lottery. And the same situation, you have a biased coin. You get heads, you have 2/3 probability of getting 3 crores. And if you get tails, which is 1/3 probability, you get nothing. Here also, the average winnings was 2 crores, and it was greater than the cost that you paid to enter the lottery, which was 1 crore. So yeah, but here you are taking a higher risk. So while you're taking decision, this higher risk did not come into the picture. So just looking at we finally thought that just looking at the averages is not a good metric to compare whether to, or not a good um, strategy to come up with decisions, optimal decisions. Then we started looking at expected utility theory. So yesterday I said that the expected utility theory basically states that uh, there exists a function u which takes output and gives a real number such that, so you have some preference strategy decision such that decision 2 is better than decision 1. This implies that probability distribution over the outcomes for decision 1 is less preferred to probability distributions over the outcomes if you take decision 2. This implies that expected utility FDW D1W is less than or equal to expected utility if you take decision 2.
So what this PD1 is, so this is a probability distribution over the decision one, but then the
Yeah,
probability distribution of which thing? I mean, probability distribution
yeah,
of
okay.
what?
Yeah, so this probability distribution is over the outcomes. So this is over the outcomes. So what you have is you have your F D omega. This gives you your outcome. The D is the decision that you have taken. The omega uh, uh, is the randomness that you see in your uh, state or your system or your environment. Based on the decision and based on the randomness, you get an output. So in these two examples, the decision was to either participate in the lottery or not to participate. So suppose your decision whole set was 1 0, then you had F1. Now the randomness omega, it could either be heads or it could either be tails, right? If you one means that you are participating in the decision in the lottery. So one means you are participating in the lottery. Zero means you are not, right? So F1H would give you 300 rupees and F1 tails would give you 0 rupees. Now you can see that there is also probability distribution over this. Now this is your outcomes. Now if I take D1, so let D1 be 1. So D1 is equal to 1. That means that I am participating to enter the lottery, right? Then my distribution PD1 of 300 is basically 2 by 3. PD2 of 0 is 1/3, because those are the probabilities with which I get these two, right? Now, sorry, this is
Yes.
PD1. This is PD1. Now, if my D2 is 0, then yeah, I hope I'm clear, right? Yeah. So yeah. So then 0H, I get nothing because I have not participated. And F0 tails also I get nothing. I have not participated. So basically PD2 0 is 1. Whatever you do, you'll just get 1. It is a direct delta at 0. You have that distribution. So now if you when you want to say what decision is better than what, you're basically comparing these two probability distribution functions in a sense. So what this whole theorem is saying that, okay, how do I know if this decision is better or this decision is better? It says that you look at the probability distribution of the outcome. You compare whether this is better or this is better. Okay, now how do I compare the possible probability distributions? It says that no need to compare the decisions, no need to compare the probability distribution functions. There'll exist a utility function. This 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 theorem just says that there will exist a utility function. Now, what is that utility function? That we don't know. That utility what does that utility function do is, if you calculate the expected utility function of one decision and other, and if you can now these are real numbers, right? These both are real numbers. There'll be some real numbers because you're calculating the expectation. So you can order them. You have suppose 3 decisions. You can order all. You can calculate all the expected utilities of all those decisions. You can order them down, and you can say, okay, this is the decision where I get maximum expected utility. And mm, what that implies is you do not need to calculate. You do not need to have a uh, know what this relation is. This relation just states that uh, probability distribution given by D1 is not as good as probability distribution given by D2. So what this finally implies is D2 is better than D1. I just write out the relation D2. So when I write down D1, the scripty relation less than or equal to D2, that means that D2 is better than D1. I'm not comparing in real numbers. I'm just saying that D2 is better than D1. Now, what this theorem does is it says you, okay, how do I actually enumerate that? By using this utility function. That is what it says. So you're not comparing these, you're just comparing these two and saying that if the expected utility is better in decision 2 than the decision 1, then decision 2 is better than decision 1. However, you you feel like this metric there exists.
So does this theorem talk about the existence of such a utility function, or
Yeah, it, it talks about existence of such utility. So there are basically two theorems. I forget the names. One theorem is the one theorem is von Neumann's and Morgenstern theorem. Von Neumann's theorem. It states what the structure of this U would be. Okay, and there is a Huber's theorem which states the existence of U. Like there'll always exist a U such that this order is preserved in all of the following three cases, given some certain assumptions are satisfied. Those assumptions I'll just write down now.
so do we have only two decisions, say D1 or D2, or we have a sequence of the decisions, and then similarly we have the sequence of the parameters W, and will
So
this,
yeah,
yeah.
so this is not only for two decisions. You could have a continuum of decisions. You could have infinitely many decisions. I've just written basing the order of using two things. Uh, so basically, what you have is you have this set of uh, okay, what do I say? You have this set of lotteries or you have this set of probability distributions, right? So you have this. So P is the set of all the probability distributions over outcomes, PD1, PD2, and so on, PDN. Now these need not be finite. I don't know. Okay, I'll go for these are finite. These are finite. You have set of finite probability distributions. They could be as large as possible, but I think they need to be finite. I think there's a theorem. which is for finite. For infinite, I think you need to satisfy some more assumptions. But the theorem that I'll be writing down today, it will be only for finite. It will not be for infinite. There's those assumptions. So you have infinite number of probability distributions. And what the theorem will say is, if you have a complete uh, transitive and reflexive relation over this set P. So when I say complete, what do I mean by complete is, if you pick any 2 points from this set, suppose I pick PDI and PDJ, right? I can say whether this is less than or equal to, or this is greater than or equal to. At least one of these two would be true. Both can be true, at least one of them would be true. What do I mean when I say transitive is, if PDI, so here when I'm, excuse me, here when I'm using this notation, it means that decision dj is better than di. How? I don't know, but I just know that there exists some relation where I can say that, okay, dj is better than di. That relation exists. So if dj is better than di, then, and suppose I also have dj, dr better than dj, right? So this gives me dj better than di, this gives me dr better than dj. Then I can say that probability di is better than decision dr. So this is transitive. And reflexive is basically PRI less than or equal to PRI. The same thing holds for both. And then I can say that decision I is same as decision J if PDI is less than PDJ, and also PDJ is better than PDI. Right. So what this is saying is, I have all these decisions and I know which decision is better, and I can compare between decisions, right? If I know that, then so basically this is what I want to know. I want to know which decision is better than what, so that I can take the best decision. So in this space of decisions, what the theorem says is, you don't need to find all these things. This is just, you can use the utility function and find the expectation of those utility functions under that decision, and you can compare those expected utilities. The 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 order is present. So basically, you're taking a set where you don't know how to compute whether one is better than other, but you know that, okay, there exists some relation saying that dj is better than di. Then instead of computing in that space, you're computing in the expected utilities function space. Is that clear? Well,
Yes, but then computing this utility function would be very difficult. Why so? Because quite possible that I may not come up with the right kind of the function.
yeah, yes. That is an open problem where people come up with different. So actually, the utility function changes depending on what problem you're trying to solve. So utility function would not remain the same for each and every problem. It would keep on changing, right? And some structure of the utility function is known, saying that it's concave and it's not, it's increasing basically. But other than that, you have to come up with your utility. There is no like hard and fast rule like, okay, this is the utility function. If you use this, then everything would be solved. Depending on how many decisions are there, what are the decision probabilities that you can take, you will see that different utility functions give you different things. Oh yeah, and also forgot to mention that. Okay, so each problem would have a similar form of an utility function. So when I mean form is that the utility function that this shows existence of, there is also a theorem for uniqueness. So the utility function would be unique, but suppose suppose there's some other u tilde which satisfies this equation. This is my equation. Then you can basically write u tilde as s1u plus s2, where s1 is greater than 0. S1 and s2 are both real numbers. So s1 is positive real number, s2 is some real number. So basically, uh, if you have a problem and there exists a u, you find an u for which these are present, right? If you shift and scale it, the ordering doesn't change. Like everything remains the same. Like you can shift and scale it to some degree. So it's more like saying you just need to find uh, yeah, you just need to find the class of utility functions. So one class of utility functions that we saw yesterday in one of the examples was we saw u of x equal to alpha x minus x square. You could have a utility function where it could be x power a into x power b with some constraints on a and b. You could have a utility function where it is, say, 1 minus e power minus lambda x with some constraints on what lambda should be. Lambda should be greater than or equal to 0. So these all are class of utility functions that you could use. So that is a more problem specific, like how much well do you want your risk to be defined, and so on, so on and so forth. So that will come slowly. So okay, so first today I just want to revisit this example that we saw yesterday, because I think I missed something, and I think you were asking something on that. So I'll revisit this. Yeah.
Yeah, so but what is the outcome of this function, say f of d comma w? So we are making a decision, and then there is an uncertainty parameter w,
Yeah.
and this function will return value, a real number or what?
Yeah. This function will return a real number.
So then instead of
This, this,
taking, instead of using,
Yeah, so this function could return a real value, could not return. I'm putting no guarantees on this giving a real number. But this utility function is something you're saying that I could just make this function the utility function, right?
how, so I mean, why to unnecessarily use u here, and why don't we directly compute the expected value of this thing if we can consider this f as a random variable kind of the thing, and
Yeah,
which
yeah.
depends on two things. Yeah.
Yeah. So uh, that's a good question. So here, when I say this function gives me an output. The output is basically giving, say, stating how much value. So in these examples, in the first example, it says that okay, you win 300 rupees, you win 0 rupees. That's it, right? Similarly, when we scale it up to 1 crore, there the same function would give you 3 crores, 0 crores, right? Now, why we are introducing the utility function is to come up with the concept of risk. Like here, 300 and 0, losing 100 rupees doesn't matter so much. So, but you need to make two differences. One difference is I want to know what my outcomes are, so I can know what my average outcome is, and I also want to know what is the utility I get given that I get those outcomes. That is a separate function. So if I directly make this fu, and I directly take an output saying that okay, I don't get 300 rupees, I directly get this, then there is no physical intuition on saying that okay, what do you mean when I say I win alpha into 300 minus 300 square? You know what I mean. Like the problem setup is you have a decision to make, you have a noise, you get some amount of money with some probability, right? This is your thing. So that f d comma w just tells you what your outcome is, how much you're winning, how much you're losing, what is happening there. Now, after that, this problem is formulated, you are coming up with an u function saying that, okay, if your output is this much, then this much utility is what you'll have. Okay, so
Yes.
I'll do one thing. I'll actually go through that yesterday's example once again, because I think I missed out some key points, which I think is what is causing the issue here. So I'll just go through this example once again. So you have 1 rupee, and then I'll be quick this time. So you have investment A, where if you put 1 rupee, you get 1.5 rupees with probability 1. And if you have B investment, where if you put 1 rupee, you get 3 rupees with probability half. and you get 1 rupee with probability half, right? So, okay, now my F, okay, so decision D belongs to the set 0 and 1. It basically says how I'll partition my investment of 1 rupee in both of these investments. So I get D into 1.5 plus D into 1 minus D with probability half, and D into 1.5 plus 1 minus D with probability half. So this is basically uh, 3 minus 1.5D with probability half, uh, 1 plus 0.5D with probability half. Now, so yeah, yesterday I did worst case scenario. I didn't do the average scenario, I think. The average scenario would be, so you're maximizing D belongs to 0 to 1 expected FDW, right? So these two equations, this FDW is directly coming from my problem statement. I have not introduced any new utility function or anything. I'm just maximizing expected outcome. This is what we did intuitively. So expected outcome is, this expectation is basically half into this plus half into this. I'm taking a half common, so I get 4 minus 0.5D, right? Now, if D belongs to 0 and 1, then I'll get the max only if D is 0. If I put anything, it will be less than 4. So the maximum value is 4, but it is attained at D star equal to 0. So what this telling me is invest everything in B. Now, if I use utility function, uh, so the utility function is this, u of x equal to alpha x minus x square. And now I do maximize D belongs to 0, 1, expectation of utility of f d omega, right? This utility, I'm introducing it later so that I'll be able to have a better idea of what the risk is, right? Okay, so
Yes, yes.
this boils down to uh, max. I'm not doing the calculation again. Um, minus 2.5 d square plus t into 8 minus alpha. And the d star that you get here is 0 if alpha is greater than or equal to 8, and 8 minus alpha by 5 if alpha belongs to 6 and 8. So here, if you see, suppose alpha is really high, right? Then what happens is this alpha x term starts dominating this minus x squared term. So you're basically, your function is linear. And if alpha is small, then you will see this kind of tapered concave increasing, but tapered. The rate would keep on decreasing function. So if alpha is greater than 8, it is basically saying you the optimal decision is same as average because your linear terms keeps dominating. So as you keep on increasing alpha, you will see that your utility function goes almost linear. And hence you get this type of solution. And I'll also give the reason of why this happens. So, okay, before doing that, I'll do I'll I'll do two things. Okay, so one is I'll I'll first state the assumptions for the theorem, right? Assumptions for the theorem. So let P be my set of probability distributions on outcomes, right? So basically, your set of probability distribution on outcomes, given that you're taking a decision, given that you have taken a decision. So if I say P1 comma P2 belongs to P, this means that there is some value. If I take some outcome P1O, this O is basically coming from F D omega. You get some zero point 0.2, and if you take P1O2, you get 0.4, something like that. You have a distribution over all those outcomes, right? Now, if I take two terms from two probability distributions from this, then alpha P1 plus 1 minus alpha P2, right? This is also a new lottery. Now, how do you realize this lottery? Physically is basically what you do is you take P1 and P2 and then you flip a coin. You flip a coin and you get heads with probability alpha. You get tails with probability 1 minus alpha. Now, uh, if it is heads, you play decision 1, which will give you a probability distribution of outcome of P1 in that thing. And if it is tails, you play P2. Okay, so now alpha P1 plus 1 minus alpha P2 of O is just alpha P1O plus 1 minus alpha P2. So basically what you'll see is this set of probability distributions is basically a convex type of set. So if you have, say, two decisions, right? Now those decisions are deterministic. Now you can make this um, random, or it's a continuum of decisions. Now you can, now alpha could be anything. It could be like 0.01 to point, like if you have P1 addition, P2 addition, you on the straight line between P1 and P2, you can have all the decisions depending on how you choose alpha. So I hope that is clear, right? So if you have P1 here, if you have P2 here, and now I can mix. It's a this 8 is compounding. So there is a new decision here. Suppose this alpha is equal to 0.25, right? Now, how do I get this decision is I pick P1 with probability 1 minus 0.25 and uh, P2 with probability 0.25. Then I get a new decision, which is not deterministic, which is random in choice. Basically, I get a continuum of all the decisions. Suppose I have P0 here, then with this I can join a line. Suppose I have P3 here, I can join lines with all of these and get a continuum of all the decisions. So basically, you're doing convex combination of all the decisions. So this,
Yes, so how do I view it that we have the combination of the uncertain events here? Like say, I flip a coin. That is
hmm,
one. I mean, one uncertainty is here. I mean, and then
y-
after getting a head, then we have another uncertainty in the form of a variable
yes,
that
yes,
I would be
yeah.
following. I would be taking the decision one.
Yes, yes, yes. Yeah, yeah. So your question is, I'm adding uncertainty to my system, right? How does
Yes.
it better me? So what I'm saying is, um, sometimes maybe it's not always. It's sometimes you will see that. So here, basically, what I'm trying to make sure is, making a decision need not always be deterministic. Like you need not always have a decision saying that, okay, I will do this if this happens, I'll do this if this happens. Your optimal decision could be of the form that, oh, maybe I'll do this with probability zero point 0.7 and I'll do this with probability zero point 0.3. Like
Right.
that
Right.
could
And
also,
sometimes,
that,
yeah.
yeah, like I'm opening you up to the fact that you could have random decisions also. And basically, the utility theorem says that you should have, like it says that you have this set of probability distributions such that you can have a convex combination that will also be in that set. like all the set. So this set of probability distributions will contain all those deterministic decisions and also uh, all the random decisions that you can make by combining 3 or 4 of those deterministic decisions in a convex. So this is basically the convex combination of all deterministic decisions. Yeah, I hope that is clear.
Yes, yes, it is clear.
Okay, so this was P. Now, my first assumption, A1, is there exists a relation, the scripted one, which is complete, transitive, and reflexive on P, on this set of probability distribution of outcomes. Now, this ordering, there just exists. What does it mean is when I say it's complete, I mean for all P1 comma P2 belongs to P. So any 2 points you take from the set P, you will either be P1 is less than or equal to P2 or P2 is less than or equal to P1. So one of these two is true. At least one of these is true. Both can be true, but both can't be false. So you can basically what it is saying is that you can order all of these outcomes in a straight line. Like you can put them all together in a straight line and you can choose, okay, this is the best outcome, this not. This is the best probability distribution on the outcome, this is not the best probability distribution outcome. This exists. And when I say transitive, I mean P1 less than P2 and P2 less than P3. If these two, this implies P1 is less than P3. Uh, okay, A2 before A2 and P2 is strictly less than P3 implies P2 is less than or equal to P3, but P2 is not equal to P3. And okay, this is similar. When I said two decisions are similar, I mean that P2 is similar to P3. This means P1 is less than or equal to P3 and P3 is less than or equal to P1. Both of these satisfy. Then I say P2 and P3, both decisions have the same, are similar. They are not equal to, they are the same, like in probability distribution ways. Okay. So, uh, yeah. Um, yeah, that's it. A2 is if P1 is similar to P2, right? Then for all alpha belongs to 0 and 1, and some P belongs to the script P, alpha P1 plus 1 minus alpha P is the same as alpha P2 plus 1 minus alpha P. So basically, if P1 and P2 are the same, are similar, then I can take any other point and I can combine P1 and P and P2 and P in the same ratios and get similar solutions. This is my second assumption. My third assumption is the same assumption as 2, but now with strict inequality. Then for all alpha and P belongs to P, alpha P1 plus 1 minus alpha P is less than alpha P2 plus 1 minus alpha P. So these both are almost the same assumptions. This assumption is called as the independent assumption. Independence assumption. Right. A4 is basically P1 less than P2 less than P3, where exists alpha belongs to 0 and 1, such that you do a convex combination of P1 and P3, you get P2. This is called the continuity assumption. So if you have P1 here, if you have P3 here, and if you have P2 here, then you can come up with some alpha such that you combine P1 and P3, you get P2. So it's basically a continuum of this. So uh, the theorem basically states this assumption one is just a normal statement saying that you have some ordering. This ordering, what does it imply is there is a way to know which decision is better than which. Like you have an innate idea that okay, decision 1 is better than decision 2, decision 2 is better than decision 3 is better than decision 4, but you don't know how to compute which of the decisions is better, right? So the utility theorem states that for all P1 comma P2 belongs to P, P1 is less than or equal to P2 implies expected utility. There exists U outputs to real such that f d1 omega is less than or equal to expectation U f d2 omega. And now, how do I choose the best decision? I maximize over all my decisions such that I maximize my expected utility and not my just my expectation. Okay, and this theorem, while we are not proving it here because it's mathematically a bit much for this course, but then what it gives is U is basically a concave and increasing function. So increasing means U dash x is greater than 0 and concave means U double dash x is less than 0. So basically you're increasing, but then the rate at which you're increasing keeps tapering off. You are going it slow by slow. It keeps on decreasing, right? So just to give a basic idea of what all this is, I'll try to draw a graph and explain it. So, okay. So now take the uh, first two examples, these two. Where was I? Yeah, these two, this example and this example. So I'll call this as problem 1, call this as problem 2. Okay. So suppose I have my 1, 2, 3, and so on. And here somewhere I have 1 crore, 2 crore, 3 crore. Okay. So now suppose here somewhere I have 100 rupees and this is utility. Okay. So 3, hmm. So yeah, so suppose in the first case, if I want to take, so I have this 100 rupee thing. This is 300, this is 200, and this is 100, right? So I win 300 with probability 2 by 3. I win 0 with probability 1 by 3. If I want to take part in this thing, right? So first I apply the utility to both of them. So suppose this is my utility for this is U 300, right? And I'll consider U0 to be 0. So now the expected utility in this case would be utility at 300 into 2 by 3 plus 0. So utility at 2 by 3 would be somewhere around here. So now as you can see here, the cost to enter the lottery is much less than the average utility that I get. So my decision here would be to enter the lottery, right? Now, as I increase this, as I go somewhere here along somewhere here, I'll have 1 crore. This is increasing linearly. The y-axis is increasing linearly. Now I'm paying 1 crore to enter in the lottery, right? But then I win 3 crores with some utility. That utility would be way less because of this concave nature of this uh, tapering down of the utility function. And if I take 2/3 of this utility, it will be way less than where 1 crore is, because here all my terms have increased linearly, whereas on this scale, it has not increased linearly. So there what will happen is the 2/3 of utility of 3 crore would be way less than the 1 crore. And there you will see yeah.
So then why don't we fix the utility function always as a log function?
That is a very good question. This is true for this problem. Now, yeah, yeah. Actually, you're correct. Like you can fix it, but then you lose to play with the parameters on like for this problem this worked, but then if I want to change it to this utility function, maybe this utility function, maybe something where it is straight and then it tapers off. If I want many, like you could come up with a case where this suits better than this. Like you understand,
Yeah.
it's of the log. It's of log, but I think people use 1 minus e power minus x lambda x and tune lambda.
Yes, that kind of the function wherein there is I mean there is a possibility of tuning the parameters, but then basically
Yeah,
it would be a logarithmic function only.
yeah. Okay, so two more. Yeah, that's a very good thing. Two more reasons why people don't do that. People, it could be done. People don't do that is because uh, you fixed this. Now you have to calculate expectation, and then you have to do a maximizing. You have to do an optimization over the utility function, right? So this will be a nonlinear utility function, and this could become really complex. So if you want to choose the best decision, then you could come up with some utility function which has easier parameters or which is easy to deal with in your problem setting. I hope that is clear.
Yes, yes, it's clear to me. Yeah.
Okay. So okay, now we'll talk about something known as measure of risk. So intuitively, we have seen how bringing in utility function gives me a measure of risk, but actually, what yeah, actually what this measure of risk is mathematically we have not yet seen. So I'll write it down. So okay, first I'll write down. Okay, so first, okay, so this let me say. Suppose I tell you that you pay me Y, uh, and then I give you, if you pay me Y, I give you utility of expected outcome. So what does it mean is I give you U of expectation of X. Oh yeah, okay. So before all this, sorry, I just forgot to mention one thing. Uh, so we have just established that U is concave and increasing, right? So there is a Jensen's inequality where expectation of U is less than or equal to U of expectation of X. This is true for any concave function, Jensen's inequality. So what this inequality states is your expected utility would always be less than your utility given that expected outcome. So what does it mean is uh,
So will it be the expected value of the utility? I mean ux with somewhere utility of
yeah,
what?
so
U of x or
utility.
something?
No, okay, so I understand your question that this expectation could need not lie in that outcome space. That's what you're saying, right?
Yes, yes. So expected
Yeah,
of some, I mean, utility of something. I mean, some argument should be passed here, isn't it?
yeah. So the argument is average outcome. So suppose your outcomes are um, uh, 1, 2, 3, 4, say 10 numbers. then your average would be 5. So you pass 5 through the utility function and get what your average is. Whereas here, oh, you're talking about this inside one.
Yes, yes, this one.
You're talking on the left. Okay, it's just u of x. So it's basically expectation of u of x is less than or equal to u of expectation of x. Okay, so I have made one mistake. This x here is basically your outcomes, all the outcomes. This x here is your outcomes, and your expectation is over these outcomes because outcomes are random. So basically, these are PDI, and this is O, and maybe this also I can put this as O. And here the expectation is over the omega, small omega. Yeah. So different expectations, but I think it's fine. Yeah. Is it clear now? So basically
Yes,
what
yes.
you're doing, you're taking the outcomes and you're applying the utility function to it and then taking an average. Here what you're doing is you're taking an average of all the outcomes and then putting in your utility function. So here what I'm saying is that, look, you don't need to worry about any randomness. Uh, I have some randomness with me. What I'll do is I'll take the average, right? That average would be same if I have the same distribution of outcomes that I have, and I say you, okay, I'll pay you the average amount. And here you're saying is, uh, I'll look at the distribution inside all the outcomes, and then I'll see what my average utility is. I don't want just the average outcome utility every time. So the utility function, so the expected value you get inside the utility function is not same as when I give you the average each and every time. So this kind of decision making, if a decision maker follows the utility function and has this inequality, this will always be true if U is concave, then basically we call the decision maker as risk averse, because he he doesn't want the average outcome always, and he's, because you're maximizing this, right? While you're doing utility function maximization, taking a decision based on maximizing this, you'll always be less than the average outcome. You'll never reach the average outcome. Yeah, so that is why you're risk averse. You won't tend to take a risk using that. And this is basically what we'll use to measure risk. How far away you are from the average outcome. So what you'll do is u of expectation of x minus y is equal to expectation u of x. So this is your expected utility, and this is the payment you make to get rid of all the randomness and say that, okay, I want average outcome. I don't want anything else. I just want my average outcome, and utility of average outcome, because you're making a payment to just get the average outcome. You subtract y, and then you come up with what this y is. This y is what gives you the measure of risk in your.
Uh, So, I mean, uh, probably I did not understand something in between. So, from the Jensen's inequality, how did you reach to this idea of risk?
Oh, okay. So yeah. So uh, 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 okay, how much risk here? That can be done in many ways. One way I'm doing is I'm saying how much far I'm looking at how much far I am from my utility of my average outcome. From Jensen's inequality, you can see that I'm always less. So any decision I take using this law, maximizing expected utility is always less than utility of average outcome from Jensen's inequality. So now, if I
Yes,
even if I maximize my expected utility, it will be less than utility of the average outcome. So I want
right.
to see how far away I am from my expected, how far away my expected utility is from utility of the average outcome. I want to see how far this is. So to do that, I just subtract
But
some number
yeah,
y to
yeah,
bring
but
it
then
down. Yeah.
but then I have a query here that, I mean, what is the intuition behind this statement that the expected value of the utility is always less than the utility of the expected value? I mean, what is the, I mean, how to interpret this statement, or is there any analogy to understand this thing?
Okay. So how to interpret the statement? Okay. So okay, I'll be more clear here. There is no anal. Okay. So the statement here is, mm, suppose I don't have any utility, right? Utility is suppose say a linear function. It is just linear, right? Then you see that my left hand side and right hand side would be equal. So if I have expected u of x less than or equal to u of expectation of x. Suppose u of x equal to x. It is a linear function, straight line, nothing else. Then this would be expectation of x, and this would be equal to expectation of x on both sides. So both sides are same. Now, what you're doing is you are only comparing here the average outcomes always. Now, as you keep on increasing the moments, and since u is a concave function, what you're doing is you're not just looking at average outcome. You're also looking at how far away my average outcome is. Like how far can I lose? How far can I win? And based on how far can you lose, you're saying that, oh, maybe the risk, it is risky to uh, uh, put it there because uh, I might lose more even if the average is very high. So I'm decreasing because the probability distribution is such that, see, it's like saying that you have some distribution with average, but the average is here, but you might lose with very high probability, or you have some probability distribution where you can lose. So you're saying that, okay, the risk is high. So this utility function, this is what shows me how risky that is. If I'm very far away from it, that means that it's very risky. If I'm very close to it, it means that it's okay. It's not that risky. I, I'm not clear maybe, but did is that does that make sense?
Yes, yes. I mean, from this discussion, what I understood is that in the
Mm.
left hand side of the inequality, we are computing the average of the utility values. And the
Yes,
average
yes.
of the utility values would always be less than I
Mm.
compute the utility of the average value.
Average value. Yes,
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 and this is because my function, my utility function, is basically a concave and an increasing
yes,
function. So
yes,
therefore, the average value will lie somewhere in the middle, and if I compute
yes,
its utility, that would be higher. Yes, I understood this
yes,
thing. Yeah, it makes sense. Yeah. Yes, yes.
yes. And basically this, okay, so now how do I quantify risk is I calculate what is the uh, highest y. Okay, so now I know that this is less than or equal to this. Now I want to see how far away this is from this. To see that, what I do is I bring this down. I have to see how much down do I bring this so that these both become equal. So I subtract a term y from this. So I calculate u, I have expected u of x. This is equal to u of expectation of x minus y. And this y is your measure of risk.
Yes.
So this method is actually calculating how far you are away from that utility of average outcome. This utility of average outcome is basically you are saying that I'll do average always. Like I'll maximize this. Okay, okay, it's this thing. It's basically this thing. But then instead of doing this, you're just putting an utility function over this. You're doing this. Your decision maker takes this. Like it does average, and then it says, okay, this is your utility that you're getting. And this is very risky. This is very risky doing the average. But then this utility function, it will always give you something which is less than this. So I want to see how much risk I've avoided or how much risk I have not avoided. So that distance gives you a measure of risk. I hope
Uh,
I'm not
yeah,
correct.
yes, I have a query here that instead of, I mean, passing this expected value of x minus y as an argument to the utility function, we could
Hmm.
have written this thing as the difference, like say, utility of the expected value of x and minus the y. And I think that will truly capture the measure of the race. So in that case, the y will become equals to the difference in between the utility of the average value minus the average of the
Oh, okay.
average of
Yeah,
all the
yeah.
utility values.
Yeah, sure. I understand your point. Yeah, that is also a metric. So you're saying you want to define some other metric of risk, which is basically saying I want to calculate expectation of u of x minus u of expectation of x.
I mean, it's reverse. So it's like,
Oh, yeah.
yeah,
Yeah. I
yes,
wrote minus. Yeah, yeah. So u of expectation of x minus expectation of u of x. Right.
yes,
Yeah.
yes.
I think okay. Okay. Here. Oh, yeah. This is also a valid measure, but I think you need to be able to compute this thing for general terms. I think okay. In the next class, I'll actually give you a closed form solution for my i-
Okay,
taking
okay, okay.
this taking this. I'll give you a closed form solution for y. It's not that easy actually. You tailors you. It's not that difficult actually. You do Taylor expansion for this and Taylor expansion for this, and you get something. You get y equal to, yeah, I don't remember, u double prime x by u prime x minus expect. Yeah, I don't remember. It's something of this form. And oh, there's a variance square. Yeah, there's a variance of x, like how much this outcome varies. X, so it's something minus variance u double prime x by u prime x. I think this is what your metric is, and it says that if you have huge variance, then you have high risk. If you have less variance, then you have less risk. Something like that. You, you
Okay.
using this metric, you get a closed form solution. Yeah, you can definitely try this out. If you can come up with a closed form solution in terms of u and other statistical things that you know of x, this could, I think there are stuff where people have used this. It's not a bad metric.
Okay, okay. So would it be possible for you to, I mean, give a small or, I mean, or if you can refer a tutorial kind of the thing wherein one simple example is given, I mean, to understand, one more simple example is given to understand this thing.
Yeah, sure. So understand the utility functions you mean. So
Yes.
similar to this, okay, similar to
One
this.
more example. Yeah, similar to this one more example.
One more example, sure. So
Yes.
in the next class, I'll do one thing then. So today, I think I'll stop it here because I'm out of material. So okay, so in the next class tomorrow. Okay, tomorrow is Thursday, right? Okay, I'll do one
Yes,
thing.
tomorrow is Thursday. Yeah.
I'll stop the recording first because stop recording. Yeah, tomorrow is a Thursday, right?